Welcome, welcome. All right, these are the 3.1 notes for Math 3, inverse variation, and the reciprocal function. Um, my recommendation, and I did this in class, is to watch this video from Khan Academy. You can find it on YouTube called Direct and Inverse Variation. It is a great review of what direct variation is, which is something that we studied in Math 1, and then also introduces the concept of inverse variation, which is what we're talking about today. So it's 10 minutes. Go give that a watch before you start these notes. All right. So to start off with, I've got two rectangles here. I have a long, skinny rectangle with a base of 72 and a height of 2. And then I've got one that's a little bit closer to being a square with a height of 6 and a length of 24. To compute area of a triangle, I just multiply base times height. So if I multiply 72 times 2, I get 144. If I multiply 24 times 6, I get 144. Take a moment and either write down the dimensions or draw at least two other rectangles that have an area of 144 units squared. Okay. So you could have, maybe you used a calculator, maybe you just did some mental math. You could have come up with, there's a ton of different combinations. For example, I could have come up with a rectangle that was 3 by 48. I could have come up with a rectangle that was 4 by 36. I could come up with a rectangle that is 8 by 18, 144 by 1, and there's some other ones in there too. If I were to look at some of these, and I have a length and a width, let's say I have 1 and 144, 2 and 72, 4 and 36, and 8 and 18. Now, I could make a list of all kinds of lengths and widths that have a product of 144. But the point of an inverse variation is that when one of the dimensions goes up, the other dimension is going to go down proportionally. Okay, so you can tell here that going from 1 to 2, I can multiply by 2. From 2 to 4, I multiply by 2. And from 4 to 8, I multiply by 2. Similarly, but conversely on the other side, from 144 to 72, I divide by 2. And from 72 to 36, I divide by 2. And from 36 to 18, I divide by 2. That is an inverse variation. Okay. So it is stated here more, let's say, in professional language here. An inverse variation is a relation between two variables such that one variable increases, the other decreases proportionally. So the important part is it has to be proportional. So as you're writing these down, take your time. You may need to pause this video to get some of the key points written down. The equation for inverse variation can look three different ways. So this can look y is equal to k over x. I can rearrange that equation so that it is x is equal to k over y. Those are equivalent. I could also rearrange this equation to be k is equal to x times y. Now we can use all of these. This first one is kind of the one that I depend on the most. But when we are using, looking at tables, I'm actually going to be referring more to this one. So they're all equivalent. I can just rearrange my equation. I get solve for y, solve for x, solve for k, and I get these three different equations. When I read this, I read y varies inversely with x. And you could actually read it the other way as well. X varies inversely with y, and it would have the same meaning. So example 1, does the table of values represent a direct or inverse variation? How do you know? And listed in the directions, it could be neither is an option also. That's not included, but that's also something that we're going to look at. And how do you know? Oops. So here's some rules that we're going to play by. If x times y equals k, all right, k stands for just a constant. So if I get like the same number over and over again, just like I got 144 in the first example, then this is inverse variation. If y divided by x is equal to k, then this is direct variation. If neither are true, then it's neither inverse or direct variation, and that's okay. All right. So when I look at table A, right off the bat, I can notice something. I notice that as x is getting bigger, y is getting smaller. That's apparent to me. So I can check for either one first. It doesn't matter. Because I can notice while x is getting bigger, y is getting smaller, I'm going to check for inverse variation first. So that means I'm looking at 1 times 12 is equal to 12. And multiplying x and y, 2 times 6 is equal to 12. 3 times 4 is equal to 12. Looking good so far. 4 times 3 is 12, and it'll work for every pair of numbers listed. Right? So this is a constant. I get 12 every time. That's k. So the answer here, this is inverse variation. It says, how do you know? Because x times y equals 12 every time. I keep getting a constant. It doesn't matter what my x and my y are. For each option there, I get 12. Okay. Now B, these numbers are frankly all over the place. So you can see as x increases, y doesn't necessarily increase or decrease. So that can throw up a red flag automatically. We're going to work through the example anyways. But I've got 20 and 17 and 42 and 44 and 40. So I go down and then I come back up and I go back down. So that's tells me that these are going to be neither. But let's look at what happens when I start calculating this. So I can start by checking some multiplication. So 1 times 20 equals 20, and 2 times 17 is equal to 34. Right there, that's enough to say, whoop, nope, that's not inverse variation, because they has to be the same number on the other side of the equal sign. 20 and 34 are not the same. Nope, doesn't work. Then I could try direct variation. Now in my directions up here on direct variation, I'm taking y divided by x, and I want that to be a constant. So let's say I try 42 divided by 3. Well, that's 14. And then let's say I try 44 divided by 4. Well, that's 11. That also is not giving me a constant. So this is going to be neither. And my reason is going to be twofold, because x times y is not a constant, and because y divided by x is not a constant. So for both reasons. For C, my x column increases. My y column also increases. I can tell that's automatically not going to be inverse variation. When I were to look at, so I'm going to kind of side note over here. If I were to look at a graph for inverse variation, the graph is always going to, as x decreases, y increases, and vice versa, right? As one increases, the other decreases. When I look at a graph for direct variation, the opposite is true. So as x increases, y increases, and I get something that looks like this. So they have kind of different shapes, right? So since when x increases, y also increases, I know that it's definitely not inverse variation. If that's not convincing for you, okay, then we can try some things, right? I can multiply to check. So I have -2 times -5 is 10. -1 times -2.5 is 2.5. Okay, nope. It's not inverse variation. The multiplying didn't work. Let's try the dividing. -5 divided by -2 equals 2.5. -2.5 divided by -1 equals 2.5. Now something funky happens here with the zeros, and we'll address that when we get to graphing later. 0 divided by 0 is undefined. But if I check the other ones, 2.5 divided by 1 equals 2.5, and 5 divided by 2 is equal to 2.5. Look, these are all constant. So when y divided by x is constant, that's an example of direct variation. And it's direct variation because y divided by x gave me 2.5. So that's just looking at tables and identifying what kind of variation, if any, that they represent. So for example 2, 3, and 4, we're going to use a very similar method. Example 2 is a very straightforward, kind of simplified version, and then 3 and 4 adds some more layers with kind of bringing in a word problem scenario and some less simple numbers. Example 2, write an equation to represent the inverse variation for x is equal to 10 when y is equal to 3. Then find y when x is equal to -6. To start, it tells me right off the bat, write an equation to represent the inverse variation. Boom. All right, so I want inverse variation. Here's my formula. Y is equal to k divided by x. Then it gives me a pair of numbers. So x is 10, y is 3. I'm going to use that to find my constant. So y is 3. I'm looking for my constant, and x is 10. I can turn this into a proportion by putting 3 divided by 1, and then crisscross multiplying. 3 times 10 is 30. K times 1 is k. So now I've got k. From here, I can write an equation. Now, an equation, just like when I'm doing quadratics or lines or anything else, my equation is going to have y, it's going to have x, and then everything else will be filled in with a number, right? I have an input value, in this case x, I have an output, which is y, and everything else is going to be numerical. So there's my equation. Y is equal to 30 divided by x. That represents everything going on in equation 2, or example 2. From that equation, if I'm given any x, I can find y, or if I'm given any y, I can find x. So the first part of this problem says, write an equation. Here's my equation. That's part of my answer. The second part says, then find y when x is negative 6. So then I use my equation. Well, y is equal to negative 5. So the other part of my answer is y is equal to negative 5 when x is equal to negative 6. The next examples are going to require a calculator. If you want to work them out beside me, and pull a calculator out or a calculator app. Example 3, on a guitar, the string length S varies inversely with the frequency F of its vibrations. I'm going to write that formula. Now, this formula can be written one of two ways. I could write this as S is equal to K over F, or I could write this as F is equal to K over S. They're the same thing. It does not matter which one you choose. I'm going to go for the second one. So the next part of the information says the frequency of a 26-inch string is 329.63 cycles per second. There's your pair of data. It gives you the frequency and the string length. From there, I can find K and write my equation. So the frequency of the string is 329.63. It's equal to K divided by the length of the string. So again, to solve for K, I crisscross multiply. 26 times 329.63, when I use a handy dandy calculator, is 8,570.38 for my constant. Having K allows me to write the equation. So F is equal to 8,570.38 divided by S. The last piece of the puzzle here says, what is the frequency when the string is 18 inches? So now I get to use my equation. So I'm asking, what is the frequency when the string is 18 inches? So we divide, and it seems that we get 476.13 cycles per second when the string is 18 inches. Now, it is important that you include your units here, right? So it measures frequency in cycles per second, so I'm going to include that in my answer. Example 4. Now, this is similar to example 3, but it has an added little piece in there that could be really easy to miss if you weren't reading carefully. So the intensity I of light received at a source varies inversely as the square of the distance d from the source. So that's where I'm going to get my formula from. The intensity I varies inversely as the square of the distance. So it doesn't vary inversely with d, distance, the square of the distance. So pay special attention to that. So I set up my formula. Then it gives me a pair of information. The light intensity is 86 foot candles. I've never heard of that type of measurement of light intensity before. Very interesting name. At 45 feet. So using that, let's find K. The light intensity is 86 foot candles when the distance is 45. Now I have to square that. When I square 45, 2025, and when I multiply that by 86, when I crisscross multiply, 86 times 2025 is 174,150 for my constant. Woo! Now that I have my constant, I can actually write my equation. And if you feel comfortable working ahead on this, please feel free. It's a great opportunity for you to check and see that you're understanding this. And then the final question says, find the light intensity at 9 feet. So I'm looking for intensity. I'm given distance. So I'm going to plug 9 in here. Remember that that's 9 squared. Order of operation says I have to do this squaring first. So I divide by 81. And I get a light intensity of 2,150. And the units here are foot candles. So the light intensity at 9 feet is 2,150 foot candles. And you might hear my phone ringing, but we're just going to let that ring. Great. Okay, so now we're going to switch gears a little bit. The title of this section is Inverse Variation and the Reciprocal Function. So we talked about inverse variation, and now we're going to talk about the reciprocal function in some pretty good detail here. So I'm going to make a side note over here. We are going to be diving in this whole unit in a new family of functions called rational functions. And rational functions are a whole nother grouping of functions that have, some similar characteristics. We've talked about linear functions before, which look like lines, and we've talked about quadratic functions before, which look like u's, and absolute value functions before, they look like v's. Well, these are going to have their own set of characteristics, one of which being the parent function is y is equal to 1 divided by x. This is also called, it also has its own name. It's called the reciprocal function. So that's what we're going to take a dive into today. We're going to look at this parent function, y equals 1 over x. What does the graph look like? What are some of its attributes? So that's just kind of a side note to give you a little scope. To graph our first parent function, I'm going to make a really large table here. We're going to look at a lot of different values. And we're going to plug each one of those x values into the reciprocal function and come up with a y value. Now, these aren't super complicated, but you may have to think a little bit about it. So this is 1 divided by x, right? So 1 divided by -3. Okay, well, that's just a -1/3. And then 1 divided by -2, that's just -1/2. Ooh, I get to graph some fractions. -1, so 1 divided by -1 is just -1. This one's worth slowing down for. So I'm going to have 1 divided by -1/2. Well, I typically don't like to divide by a fraction because it gets a little confusing. So when I rewrite that, I'm going to instead multiply by the reciprocal. So instead of dividing by -1/2, I'm going to multiply by -2/1. Dividing by a fraction is the same as multiplying by the reciprocal. So in the reciprocal, my denominator becomes the numerator and my numerator becomes the denominator. Well, this just gives me a value of -2. The next one, I have 1 divided by 0. Now, it's easy to forget, but when I have a 0 in the numerator, that is undefined. You can always verify that by plugging in your calculator. When you do 1 divided by 0, you get an error message. Here I get 1 divided by 1/2, which again, I'm going to multiply by the reciprocal, so I get a +2. 1 divided by 1 is 1. 1 divided by 2 is a half. 1 divided by 3 is a third. I'm going to graph this. My squares on my graph paper here are really small. So I'm going to use 2 boxes to equal 1 unit. If your boxes are larger, you might use, 1 box equals 1 unit. Do whatever works best for you in your graph paper. But here, I'm going to count this as 1, 2, and 3. So hopefully this is large enough for us to actually read and make some good use out of. Okay. I'm going to go through and plot each of these. So remember, X, I always go left to right first, and then up or down Y. So -3, and then down a third. Be right about here-ish. -2 down a half. -1 down 1. -1/2 down 2. And then I hit this undefined thing. So I've plugged in 4 points in this kind of section of the graph. If I were to plug in more points, you would see that when I plugged in -4, I get -1/4, right? And that number gets closer and closer and closer to 0. So this graph kind of looks like this. Then I have this weird thing that happens at 0. It's undefined. We'll come back to that. But then my next point is 1/2, 2. So over a half, up 2. Over 1, up 1. Over 2, up a half. Over 3, up a third. Now I know I'm graphing that a little quickly, so feel free to pause if you need to. Make sure you get it all down. I get this. Now, this is one of the first non-continuous functions we've really looked at in math. And we're going to see more of them as we go. But this function doesn't exist everywhere in the domain. So as I look, and I'll use my cursor so maybe you can see it. Okay. So as I look to the graph to the left here, this red pink portion over here, it's going to go to the left, 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 left. And it's going to get closer and closer and closer to this x-axis. Now, in theory, it's actually never going to reach it. Because even when I pick a really negative number like -100, 1 divided by -100 is still negative 0.00, nope, negative 0.01. And that gets me really close to 0, but it doesn't actually ever get me there. So we come up with this idea of limits and approaching a number, but never actually reaching it. Which falls into this idea of an asymptote. So you're going to notice here where my cursor is that this part of the graph is going to approach the x-axis from below, but it's never going to actually touch it. And then when I look at the x-axis on the right, the same thing's going to happen on the other side. So as this red part of the graph continues, it's going to get closer and closer and closer to that x-axis without actually touching it. So this invisible line that this creates here on top of the x-axis is called an asymptote. And the equation of this asymptote is y equals 0. Now, asymptote has a silent p in there, so check that out. The same thing happens when I look at the graph vertically. So when I look at the graph as it comes down, 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 the same thing's going to happen here. It's going to approach the y-axis from the left, but it's not ever going to touch it. And then from above, in theory, I'm going to approach the y-axis from the right-hand side, and it's never ever going to touch it. So I have another asymptote in here, right on top of the y-axis. And the equation of a line on top of the y-axis is actually x equals 0. So don't be tricked by that. So we have these two asymptotes. They work as these invisible lines that we usually draw dashed. And they guide the graph kind of around them. So now we'll move into our conversation of domain and range and how that's affected by this idea of asymptotes. So far the continuous functions that we've looked at have had a domain of all real numbers, at least the ones that we've studied thoroughly. Here, that is no longer the case. So domain, set of all x values for this function. As I look to the graph, to the left, 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 it goes on forever. And as I look to the graph to the right, it goes on forever. But there's a spot where this doesn't exist. Because of the nature of 1 over x, when I plug in 0, 1 divided by 0, the graph does not exist at x equals 0. That's why I have an asymptote. So the domain is, interestingly enough, going to be all real numbers except 0. And simply because I just can't divide by it. And depending on what method I'm using to write domain and range, it could look different. And we'll kind of explore that later on. But for now, we're going to stick with just this kind of simplified explanation. Now, when I look at the range, so when I look down, this graph continues forever and ever and ever. It never stops. It goes down to negative infinity in the y direction. It comes up. It gets really close to the x-axis, but it jumps over it. And then it goes up, 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 up to positive infinity in the y direction. So again, it's going to exist everywhere except for right here where I have 0, because I can't divide by 0. So my range, similarly, is going to be all real numbers except 0. So this is the reciprocal function. It will always be true of the reciprocal function. Remember, the reciprocal function is just the parent function for rational functions, which we're going to be taking a deeper dive into the next section, 3.2. Phew, okay. One more example to look at. We're going to be looking at how transformations affect the rational function, the reciprocal function. And so this example 6 right here is just kind of an introduction to get you start thinking about and noticing some things. I'm going to utilize Desmos as a tool to kind of get us to discover how this graph moves. So if we look at the parent function y equals 1 over x and compare that to the example I have written in problem 6 here, g of x is equal to 1 divided by x minus 3, all plus 2. So I've added some parts here, right? So I've got this minus 3, and we're curious to see how that's going to change the graph. And I've got this minus 2. I'm curious to see how that's going to change the graph. So I'm going to head over to Desmos and kind of show you what we've got here. I've already plugged these in. All right, so right now the one that you're looking at is y equals 1 over x. All right. It's graphed there in red. This is the same thing that I just graphed, right? So I have the point 1, 1, I have the point -1, -1. And this graph just gets really close to the x and y axis and doesn't actually touch it. So if I zoom out a whole bunch, right, you can tell that it's just gonna kind of lie right there. It doesn't really go off of its rails or anything. All right. Cool. Now, when I plug in the new equation here that I wrote for example 6, I'm going to make it show up. I'll put this one away so that it's not so confusing. You can kind of see the behavior here. So as I look to the graph to the left, it looks like it approaches y equals 2. As I look to the graph to the right, it looks like it also approaches y equals 2. So you can kind of see that there's probably an asymptote right here at y equals 2. So I've shifted up 2. And then also, instead of having an asymptote here at x equals 0, which is along the y-axis, you could tell that the graph tends to approach 3. X is 3. So this vertical line right here is going to be x equals 3. This horizontal line is going to be x equals 2. Now I'm going to come back to this graph again, but I want to kind of use that material over here. The question does ask me to graph. Okay, so we talked about from the graph we had these asymptotes, and I had an asymptote here at, it appeared to be that I had an asymptote here, which is the line y equals 2, and it appeared that I had an asymptote here at x equals 3. Now I'm going to go back again and take another look and make sure that that's accurate. I'm also going to find some of these anchor points to help me graph. So what I'm referring to is I'm looking for some whole number coordinate point that's just easy for me to graph. So right here, I've got this point 2, 1. Right, I'm going to use that as an anchor point. I hit this coordinate, but then I don't actually hit another whole number coordinate. And similar over here. So I hit 2, 1, and then I also hit 4, 3. I'm going to use those to help me graph. All right, and this was right. Yeah, yep, looks good. So 2, 1. And then I'm just going to use this to kind of sketch the rest. So I know I get close to the asymptotes, but don't cross them. And I'm just going to kind of stay within these lines. If you can imagine like a perfect driver trying to make this turn and staying within its turning lane. And then also for 3, right, it just kind of travels along these dashed lines, but it doesn't actually cross. Now these lines, how this graph moved. Where do these come from? So in my equation, I have 1 divided by x minus 3. Hopefully you can recognize that this graph actually moved right 3 units. Instead of having an axis of symmetry at 0, if I can compare the two, right, if I have this vertical line here, then I actually moved right 3, and then this horizontal line, y equals 2, actually came from y equals 0, so I moved up 2. So I've just kind of got these movements happening. Now this question asks me to identify asymptotes, domain, and range. All right, so domain, I'm looking at all of the x values. So when I look to the left and to the right, it appears to go on forever, except when x is 3. That's where my asymptote is. Imagine I go to the equation and I plug in 3 for x. That gives me 1 divided by 0, which is undefined. That's why I have an asymptote there. So my domain here is going to be all real numbers. My exception this time is 3. Feel free to pause and slow this video down as much as you need. Similarly, I have a problem in my range. I can't say it's all real numbers. As I look down, it goes on forever. As I look up, it goes on forever. But I have this gap right here where the graph does not exist when y is 2. So this is going to be all real numbers, except 2. Now I've color coordinated these things on purpose here with thought and intention, because these are not coincidences. This right 3 and x equals 3 and x equals 3 and all numbers except 3 is not a coincidence. Those are all going to match. All right. And then the same thing here when we're talking about the y values, right? I went up 2, so this is a y2. My asymptote is y equals 2, and the range is all numbers except 2. That's how it's going to work. And we're going to look at problems like example 6 more in 4.2, but needed to get you some exposure to what these transformations look like. Okay, awesome. Thank you so much for joining me for these notes, and stay well.